is Suresh Venkatasubramanian.
Pretty good.
And he's an assistant professor at the School of Computing at the University of Utah. Before that, he spent some time at the Information Visualization Research Group at AT&T Labs, and he got his PhD at Stanford.
Oops. Don't need to see that, do you? So I just want to thank the organizers for having me over to talk to you. My background is in algorithms and data mining, so this is, in contrast to some of the talks I've seen in the last couple days, is a bit more of a low-level talk, a technical talk. One of the things I like to do is think about computational models, algorithm models for thinking about large data. We've seen a number of ones in the past. You've heard about them, things like streaming algorithms and even external memory models, MapReduce models. And so this talk is really about trying to think about how to do learning in a certain kind of distributed model. And so the mechanics of a typical sort of a old-fashioned, if you wish, learning algorithm goes something like this. You have some training data, you have a learning algorithm that tries to learn some kind of model. So you run your learning algorithm on your training data and you get a model out of it. And then you get some test data and you can make predictions. So this is what is typically called a batch learning model. It's a sort of a standard way of at least designing machine learning algorithms. And of course, in a real-time or online setting, you want to make predictions as the data comes in. You don't want to have this training and test sort of situation, which is good for writing papers, but it's not good for actual learning. And so you typically have a much more interactive model where you have training data, you have learning, you have a model that's constantly being updated as the data comes in, and you get predictions. This is, of course, called online learning and other terms for this. But in all of this, there's this basic assumption that you have. And the assumption that you have is that, well, you have the data. That the learning algorithm can access the data whenever it wants to and however it wants to, and it can do whatever it has to do. In fact, the main bottlenecks here are usually the computational bottlenecks. That a lot of these learning algorithms involve sophisticated optimization, and that's where the work is in actually doing this. You can think about a more distributed model, if you wish, for data, where you can say, well, I have access to a number of cores, and maybe I have access to a cluster, and I want to build my learning algorithm to take advantage of this. So you take your data, and you distribute it among a number of different nodes. Each node gets a different part of the data. You can maybe do some learning on the individual nodes and try to combine them in some way. So you may get a model parameters for each of the individual data sets, and you combine them. But even in this case, what you're doing is you have an explicit plan to distribute your data, do something clever, and bring it back to you. What I want to talk about today is how you might do learning in a situation where your data itself is intrinsically separated. You just don't have access to, you don't have the ability or the access to all the data at any one time. And of course, there are many places where this happens, right? So data can be distributed geographically. If one of the things we do is we work with folks in the atmospheric sciences group in Utah, and they have access to these monitoring stations all over the country. And this are producing measurements every 5 minutes. And while you would like to get access to all the data, do some learning on it, you really can't physically ship everything over to one location. Right? They happen to be where they are. You may be a large company with many data centers, and you have data accumulating across your data centers, and you want to do some analytics across the data centers. Again, you don't have the ability to move the data to some central location or set of central locations where you can do analysis on it. Even on the level of a single machine, right, you have multi-core systems. And in multi-core systems, what you want to do is have the push in multi-core systems to have little data caches right next to the processing units. And while it's not a bad thing to transfer data across cores, it's something you would prefer not to do, because it takes a bit longer, there's latency involved. As far as possible, you like to distribute the computation locally. And of course, there's a dual version of this, where instead of taking the memory and putting it next to the core, you take the core and put it next to the memory. There's things called PIMs, there are processor memories, where the memory chip itself is a small computing unit attached to it. And again, you want to have the memory and the processing units together, you don't want to have them separate from each other. So whether you think of it this way or whether you think of it geographically, the point is that what you want to do is keep your analysis close to data. So Alex Sally's talk, he had this nice statement where he said that you want to push the analysis close to data. You don't want to have the analysis far away from data. That's sort of the theme of what I'm talking about. And so how can you learn in an environment where communication, transferring data across nodes is either very expensive or is undesirable? And how do you actually move this analysis to data? How do you learn in a communication-restricted environment? So I posted a paper on this a little while ago, and some people on Twitter started commenting on other names for this. So one name was learning without chatter. Another name was just shut up and learn. So there are a couple of different ways to think about this. But this is the basic setting. You have a communication restricted environment, and you want to learn. And so what I'm going to do now is describe what you might think of as a somewhat toy problem, but it's a problem that, at least from an algorithm's point of view, helps understand the complexities of the model, the kinds of tools we can build, and how we can design things to do well, and prove things that things work well. So the simple model I'm going to think about is the following. You have k players. So each player owns a certain amount of data. And there's an implicit union over all this data, the total data set D. And you have some learning task. You have some desired solution to the learning task, and you are measuring the quality of solution, some error or loss or risk term error. Right? And so, of course, your goal is to compute the solution H to the learning task T, which has small error. But in our setting, what we're going to say is that we give you some tolerance parameter, some epsilon. What we'd like to do is have the players talk to each other in some way and come up with an answer that is as close as possible, mediated by your parameter, to the answer you would have if you actually had all the data points. So you can think of the right-hand expression error as the optimal answer. If you had all the data, the left-hand side is the answer you're going to produce from your communication protocol, and you want them to be close. And you want to do this, obviously, with as little communication as possible. Okay, so that's a setup. And so in order to, for the rest of the talk, I'm going to focus on a very specific learning task with a specific solution, a specific kind of error. Okay, and hope to bring out some general principles. And by the way, I should say, feel free to interrupt if you have any questions, but especially about the model and the assumptions I'm making. So the task we're going to be looking at is a very simple task of binary classification. I know many of you are familiar with it already. I'll just do a brief overview because we have a very broad audience. So in a binary classification task, you have points. This is a supervised learning task. So points are labeled. They're either a plus or a minus. For example, you might be trying to classify the gender of tweets. This is some project work that I recently heard about, where you're trying to sort of look based on a sequence of tweets, can you classify the gender of the person? Maybe you're looking at Amazon reviews and actually what they call label whether a review is positive or negative. This could turn out to be important if your automatic algorithm can't tell the difference. And so you're given this data, and what you want is some kind of rule that, given a new example, will classify it. Right? And so your rule might be some kind of line. And we for example, we saw examples of this in my studies. So you have some rule, and the rule says, okay, if I have, this is my rule, and if my point lies on one side or the other of this line, I can tell it's a plus or minus. And typically what I'll be talking about is what is called a maximum margin classifier, a classifier that separates the two sides as much as possible. Such a classifier, of course, can be described by some kind of vector. You can, in D dimensions, there's some weight vector W and some shift vector B that describes this object. And you can also describe this by support points. So either by a vector or by support points, you can describe, so these are the model parameters. And you put them in there, and so basically the support points say, okay, there's one support point holding the classifier this way, there's two support points holding it the other side. And again, it doesn't really matter for the purpose of discussion which way you think about it, there is some model parameter you can use. So what is the error of such a classifier? Well, this is a good classifier. It separates all the pluses from all the minuses. But you may not give a good answer, you might give a bad answer. In this case, you have some points that are misclassified. And so for now, there are many ways of thinking about this, but we will talk about the misclassification error as a fraction of mistakes you make. That is my loss term. And so in my distributed setting, what I like to do is come up with a classifier that has a misclassification error as close to the optimal solution as possible. Okay. All right. So it turns out that if you have some control of your data, if you can distribute your data any way you want, then you can do all kinds of things. And so there's some standard machinery in machine learning that's called the theory of BC dimension. And I won't go into detail, but roughly speaking, for spaces that are well behaved, and linear classifier spaces are one such space, essentially you can do the following. If you have two players, and they both have data, and you want to learn some kind of joint classifier, obviously you don't want to transfer all the data from one side to the other. That is too much. But here's what you can do. You can pick a random sample from one side. So you're one player, I take a random sample of my data and give it to the other player. And say, now you go and classify my random sample with all of your data. So the other player classifies the data along with the random sample. And because of the properties of the space as controlled by this thing called the BC dimension, you can prove that any classifier the green player gets will only make a small mistake on your data because of the way you chose. And it turns out you can choose sample very just uniformly. But because of the fact that you chose a random sample and the structure of the space, you will not make too many mistakes. Okay? formally, what you can say is that roughly, and it's a bit for a load on there, you need something like d over epsilon times log 1 over epsilon samples, okay? In order to guarantee that the error you make is only an epsilon in the misclassification. And one important thing to note here is that this is independent of the size of my data, right? The sample size is independent of how big my data set is. It only depends on the error parameter I wish and the intrinsic dimension of the space. And that's a very powerful result. It's a basic result in sampling. And just to get used to this, sometimes it's hard to parse things like d over epsilon, log 1 epsilon. I find it often useful to replace 1 over epsilon by a number r. So here you have bounds which look like dr log r, where r, which is equal to 1 over epsilon, is kind of like your penalty threshold, penalty number. So the n is, of course, a normal size of input kind of number, but 1 over epsilon is another kind of error number that you typically work with in these spaces. Okay. So if you have randomly partitioned data, this works very well. And even if your data is adversarially partitioned, so the adversary is choosing who's what, the sampling can work. However, the bounds you get are linear in this error parameter. And the question, of course, is can you do any better? Can you actually reduce the size by a lot? Because, for example, if you want 0.1% accuracy, this 1 over epsilon is 1,000, and along with constants, you can get pretty large. So you'd like to do a lot better. And it turns out you can, and the reason this happens is basically, I think, the reason we know who are the boring people at a party and who are the interesting people. In short, a dialogue is exponentially better than, more informative than a monologue. And what this means formally is the following. If I have a bunch of players, and if I have, say, 2 players, the 2-player protocol went like, I talk to you and tell you stuff and you go do something. This is a one-way protocol. You didn't say anything back to me except for giving me the final answer. It turns out that if you're only allowed to do that, if you're only allowed to have one player talk to the other, you can prove, and using techniques from theory called communication complexity, you can show that you cannot do much better than what we just described. Maybe a little bit better, but not much better. There's a lower bound of this. You have to send a certain amount of information. But if you're allowed to have the players talk to each other in a true sort of uniform distributed protocol, you can do exponentially better. So instead of 1 over epsilon examples, you need log of 1 over epsilon examples. And the idea behind this is a kind of a nice idea that I think is a good trick to think about how to design distributed learning methods. And so I want to spend the rest of the time telling you a little bit about that idea. Okay? So hopefully the result is clear. The idea is that if you allow players to talk to each other in a truly distributed setting, you can do exponentially better than, say, a one-way communication. And the idea behind this is adaptivity. So let's think of a thing that you are all familiar with, binary search. So how does binary search work? You have a bunch of points and you want to search for a particular point. And I'll assume that this is a sorted list. So at some point, if you're playing 20 questions with someone, you say, okay, is it the middle point? And the other person either tells you, no, it's less than, or no, it's more than, or it's the right answer. Which one? So suppose the person says, no, it's the right answer is more than the one you asked me. Go right. So you go right. And in doing so, you eliminate everything that came before. And of course, you're doing this analysis, you know that binary search takes log n times. The point of this is adaptive. The adaptivity in this process allows you to prune out things very quickly, so that very quickly you can hone out the right answer. But there's actually another way of thinking about this. Another way of thinking about this is to say that initially, there is some kind of uniform distribution, some uniform prior on where your point would be. And after asking the question, you can update that distribution. The distribution is now more heavily weighted in the region you have not yet explored, and is less weighted in the region you have explored. Okay. So there's this technique that's very popular in machine learning. It goes by the name of multiplicative weight updates. It's also known as boosting for some people. I like to call it zombie binary search for reasons I'll explain in a second. Suppose you want to do classification, and you have one player who has a bunch of points. You can't see them, so they're kind of hidden away. That player offers you a classifier, says, here's my answer, tell me how good it is for you. And you look and say, no, that can't work. I've got points that are mistaken here, and there are points that are mistaken there. You gotta do something about this, you gotta fix this. I could send those points over, but for the usual reason I can't, because there could be many of them, and I don't want to send them all over. So I do something less. I say, well, I am merely going to update my importance on these points. I'm going to increase their weight. And then I'm going to randomly sample from my set and give you a couple of points back. I might give you points that you correctly classified, but I'm more likely to give you points that you have not correctly classified. So you can think of it as zombie points. You want to get rid of them, but they keep coming back. But the hope is that over time, you kill them enough times, it'll get it right. That's why I call it zombie. And then this goes on. So the player 1 computes a classifier, player 2 finds mistakes, updates its weights, picks a sample, gives it back to player 1, this keeps going on and on. And what you can prove is that after only log 1 of epsilon steps, the D just comes from the dimensional space, you can get an epsilon optimal classifier through this adaptive process. Suppose you have multiple data sources. You could imagine doing the same thing by saying, okay, I'll have the coordinator talk to one player, talk to the next player, talk to the next player, and so on and so forth. There are two problems. First of all, different players have different amounts of data, so your analysis can get skewed. Also, once the coordinator solves a problem with one player and starts working on the protocol of the next player, it might corrupt its answer for the previous player, because it doesn't really know what data the other player has. So it turns out you can take the same protocol and adapt it to work with all nodes talking to the coordinator simultaneously. The basic way it works is each player reports their weight to the coordinator tells them what fraction of the input they actually own, then they run the two-player protocol, one step of it in parallel, and this goes on. And again, you can show that with roughly the same number of rounds, you can learn an epsilon error classifier. Okay. So this works for classification and for binary classification. Not necessarily, it's a nice problem, but it's only one such problem. But it turns out the techniques work in general. And so one way to think about this is to say, well, there's a strong connection between learning and optimization. So a lot of learning problems can be formulated as a convex or non-convex optimization problem. And more abstractly, you can think about this as saying is that each player owns a certain set of constraints. Often these constraints come from points, or they can come from other sources. But you have different players owning different sets of constraints, and what you want to find is a feasible point that satisfies all constraints simultaneously. But you don't want to actually have to transfer all the constraints back. And it turns out that using another paradigm, the idea of streaming algorithms, you can actually solve this problem in a distributed setting. So a brief overview of streaming algorithm is an algorithm where you scan the data coming in, you're allowed some working storage, but the working storage is sublinear in the size of the input. You're not allowed to store the entire input. You're to store something significantly less. And one way to think about a streaming algorithm is as a communication. A streaming algorithm really is a communication between the first half of the stream and the second half of the stream. Because what happens is that the first half of the stream comes along, you store some information on your work tape, a small amount of information, and that is given to the second half of your stream. And this is used for proving lower bounds in streaming algorithms. But it's also useful for showing upper bounds, and I'll just show you. So briefly, what you can show is that any streaming algorithm can be converted to a distributing algorithm. There are certain parameters involved in this. They're not that important, but you can use this idea of communication to convert it. And therefore, you can do a distributed algorithm for linear programming, for example. If you have a bunch of constraints distributed among different players, you can find a point that satisfies all but an epsilon fraction of the constraints using very small amounts of communication, again, independent of the number of constraints in your system itself. Okay? And there are variations as well that apply for semi-definite programming as well. So what I wanted to convey here is this idea of how to think about large-scale distributed learning and focusing on communication only. I'm not saying that computation is not important, but like with most models, it's helpful to focus on the thing that's the biggest bottleneck in order to understand how that challenges how we design algorithms and how to come up with good design principles. And it's of course relevant to both big data and what I like to call big iron, all the HPC stuff with these big cabinets. It's crazy, it's the secret around there. And what's interesting is the techniques that you can use to solve this problem, and hopefully there'll be more techniques coming along. And there are many problems that one can look at. Some of these that we're looking at right now is distributed clustering, multi-class learning, dimensional evolution, PCA. We heard this about this nice robust incremental PCA method from Alex Elia yesterday. I'm also interested in general optimization and even lower bounds. What kind of limits are there on what you can do in this kind of model? So I think I'll stop there. I have a couple of references. There's a paper at AI Stats this year, and there's another one that's on the archive. I would like to also shout out another paper that's coming up in Code by Balkan, Bloom, Fine, Mansour, which is basically dealing with precisely the same model, and they're looking at problems of privacy preservation as well, among other things in this instance. So there's a growing interest in these kinds of problems in machine learning. I think it's worth further study of how to think about communication optimal learning in large instances. And with that, I'll thank you all for listening.
All right, any questions? Whoa.
I was just wondering how do you create your algorithm from AWS? It seems pretty similar.
So in fact, like I said, since we're using the boosting framework, we are essentially implementing boosting in a distributed setting. So one of the insights is that you can actually do this in a systematic way. Some of the details that I have left out of the description, is that in a distributed setting, to maintain your distributions and to do your sampling properly, you need a couple of tricks from distributed computing that distributed sampling methods that we use. But for the most part, as a design principle, if an algorithm works in the boosting framework, you should be able to mostly adapt it to work in a distributed setting. But like I said, there are other ideas that come up as well, like streaming algorithms, that are nice to use.
Can you say a little bit more about your reduction between a streaming algorithm and a distributed
Right.
learning algorithm?
Yeah. So if you think of the simplest case of a two-player distributed model, okay, and you can generalize this. So think of your streaming algorithm. So the streaming algorithm is your tape is moving, the data is streaming along, and your machine is monitoring it. Think of what happens if I stop the data after, let's say, n inputs or some number. Let's say after the first 100 bits, I stop. Okay. At some point, I have some intermediate storage in my working tape and some state of my machine. That storage, by the definition of a streaming algorithm, has to be sublinear, otherwise it's not a streaming algorithm. So let's say I have a polylogarithmic amount of words in my working storage. Now I take that working storage and give it back to the second half of the stream, which is owned by the second player. Okay. So that's the communication of the first half of the second half. So if you think of two players running this protocol, the first player essentially implements that same streaming algorithm on their data. When it stops, they take whatever working storage they have, send it over to the second player. The second player starts up its streaming algorithm with that working storage and then completes. So essentially in this distributed model, you're not simulating the streaming algorithm. If you have k players, you chop it into k pieces and so on and so forth. So you can do much more in a distributed setting than just this, because the individual players don't have to be streaming players. But since there's so much work on streaming algorithms, it's a good way to quickly generate an algorithm, and then you can see how to make it even better. But this at least gives you an upper bound proof of concept design. Does that make sense?
Thanks for the talk. It was really nice. I'm wondering, sort of, how fundamental do you think your lower bounds are, and why did you choose to sort of use a protocol where you're shipping data between different agents in your system as opposed to shipping the different parameters or something like that?
I don't care what I share between. I don't care what I share between players. The communication lower bounds are I don't care. It's just this. So in fact, in this protocol, one player is sending classifiers, the other player is sending points. So they're not just the one player is sending a model parameter, one player is sending points. So I don't really care. And that's one of the beauty of these communication complexity-based protocols. You don't, at least from a lower bound point of view, I don't care what you're sending. I can give you strong limits on that. And from an upper bound point of view, again, I don't really care what I send. I just have to design it right.
All right, we'll take one more question.
Thank you. I thought it was a very interesting approach.
Thank you.
Now, you had mentioned several applications at the beginning of your presentation, so I was wondering if you've been able to apply it to those applications of data centers.
Right. So we've done some proof of concept implementations, but there is sort of deployment implementations. In fact, one of the groups at Utah, that is, we have a group called Emulab that is part of the big GE and they build a lot of virtual networks for people. We've been talking to them about actually deploying this and seeing what are the real problems that come up when you actually do this across a network, and that's one thing we'd like to try and do there.
All right, let's take one more round.
Thank you. He's designing machine learning algorithms. And of course, in a real-time or online setting, you want to make predictions as the data comes in. You don't want to have this training and test sort of situation, which is good for writing papers, but it's not good for actual learning. And so you typically have a much more interactive model where you have training data, you have learning, you have a model that's constantly being updated as the data comes in, and you make predictions. This is, of course, called online learning and other terms for this. But in all of this, there's this basic assumption that you have. And the assumption that you have is that, well, you have the data. That the learning algorithm can access the data whenever it wants to and however it wants to, and it can do whatever it has to do. In fact, the main bottlenecks here are usually the computational bottlenecks. That a lot of these learning algorithms involve sophisticated optimization, and that's where the work is in actually doing this. You can think about a more distributed model, if you wish, for data, where you can say, well, I have access to a number of cores, and maybe I have access to a cluster, and I want to build my learning algorithm to take advantage of this. So you take your data, and you distribute it among a number of different nodes. Each node.
Speaker is Suresh Venkatasubramanian.
Pretty good.
And he's an assistant professor at the School of Computing at the University of Utah. Before that, he spent some time at the Information Visualization Research Group at AT&T Labs, and he got his PhD at Stanford.
Oops. You don't need to see that, do you? Things like streaming algorithms and even external memory models, MapReduce models. And so this talk is really about trying to think about how to do learning in a certain kind of distributed model. And so the mechanics of a typical sort of a old-fashioned, if you wish, learning algorithm goes something like this. Right? You have some trained data, you have a learning algorithm that tries to learn some kind of model. So you run your learning algorithm on your training data and you get a model out of it. And then you get some test data and you can make predictions. So this is what is typically called a batch learning model. It's a sort of a standard way. So I just want to thank the organizers for having me over to talk to you. My background is in algorithms and data mining. So this is, in contrast to some of the talks I've seen in the last couple of days, is a bit more of a low-level talk, a technical talk. One of the things I like to do is think about computational models, algorithmic models for thinking about large data. We've seen a number of ones in the past. You've heard about